Most of us are acquainted with guitars, which have metal wire wound tightly over a fretting board. Plucking the wires or strings gives us tons of different qualities. Unfortunately, while tuning a guitar, if the string breaks, we can notice that the total tension placed on the instrument changes. The string moves up and down like a whip. Waves can be progressive or standing. Let's look into the details. What is a progressive wave or a traveling wave? A wave that travels from one point of the medium to another point is a progressive wave or a traveling wave. They may be a longitudinal wave or transverse wave. Let us concentrate on mathematical description of a traveling wave. As we discussed earlier, a wave is a function of both position and time. Such a function at every instant should give the shape of the wave at that instant. It should also describe the motion of the constituents of the medium at every location. Now let us consider a sinusoidal traveling wave, since it means that the corresponding function must also be sinusoidal. For our convenience, let us take a transverse wave. The position of the constituent of the medium is denoted by x. The displacement from the equilibrium position may be denoted by y. Then the sinusoidal traveling wave is then described by y of xt is equal to a sine kx minus omega t plus phi. The term phi is considered as a linear combination of both sine and cosine function. Y of xt equal to the displacement as a function of position x and time t. A is the amplitude of the wave, omega is the angular frequency of the wave, and k is the angular wave number. To understand clearly, consider a fixed instant at t is equal to t naught. Then the argument of the sine function can also be described as y is equal to a sine kx plus phi. This shows that the shape of the wave at any instant as a function of x is a sine wave. Similarly, take a fixed location x equal to x naught. Then the argument of the sine function can be described as y is equal to a sine minus omega t plus phi. This shows that the displacement y at a fixed position thus varies sinusoidally with time. That is, the constituents of the medium at different positions execute the simple harmonic motion. Finally, as t increases, x must increase in the positive direction to keep kx minus omega t plus phi constant. Thus, the equation represents a sinusoidal wave traveling along a positive direction of the x-axis. In case if we consider a function y is equal to a sine kx plus omega t plus phi, then this function represents a wave that is traveling in a negative x direction. Now let us visualize the graph of the traveling wave. The diagram shows the plots of y is equal to a sine kx minus omega t plus phi for different values of time differing by equal intervals of time. Here the point of maximum positive displacement is called the crest and the point of maximum negative displacement is called the trough. First, to see how a wave travels, focus your attention on a crest in the figure A. This crest is shown by a cross in the diagram. We can see how the crest progresses with time in the next figure. In the second figure, the crest moves a little with respect to the first one, and a similar progression can be noticed in the following figures C, D and E. Now let us visualize the traveling wave through the motion of a particular constituent of the medium at a fixed location, say at the origin of the x-axis. Concentrate on the solid dot at the origin. We can notice the solid dot at the origin moves periodically with respect to time. This means that the particles at the origin oscillate about their mean position as the wave progresses. As we notice, from first wave, the solid dot moves periodically, and in last, it came back to its position, which shows that it completed one oscillation. We can also see that during the time the solid dot has completed one full oscillation, the crest has moved further by certain distance. Let us define several quantities using this graph. Amplitude and phase. The amplitude and phase together describe the position of the particle. The displacement y varies between plus a and minus a, since the sine function varies between +1 and -1. Then taking a to be any positive constant, a represents the maximum displacement of the constituents of the medium from their equilibrium position. It is called the amplitude of the wave. Not that y can be positive or negative, but a is positive. The argument kx minus omega t plus phi is called the phase of the wave. For given amplitude, the phase determines the displacement of the wave at any position and any instant. Clearly, at x equal to 0 and t is equal to 0, the phase is phi. Hence, phi is called the initial phase angle. By suitable choice of origin and initial time, this can be 0. So, we can drop phi from the equation without loss of generality, which means it does not affect the equation in general. Wavelength and angular wave number. The minimum distance between the 2 points having the same phase is called the wavelength of the wave, usually denoted by lambda. The wavelength is the distance between two consecutive crests or trough in a wave. Taking phi equal to 0, the displacement at x equal to 0 is given by y is equal to a sine kx. Since the sine function repeats its value after each 2 pi change in angle, we can represent sine kx as equal to sine kx plus 2n pi. We can also be represented as sine k of x plus 2n pi by k, which implies the displacement is the same at the point x and x plus 2 pi n by k, where n equal to 1, 2, 3, etc. The least displacement between the points with the same displacement at any given instant of the time is obtained by taking n equal to 1. Therefore, the lambda is given by 2 pi by k. K is the angular wave number which represents phase change per unit path difference. It has SI unit of radians per meter. Period, angular frequency and frequency. Now let us consider the displacement of an individual element with time. We can take phi equal to 0 and x equal to 0 for convenience. Then we once again get a sinusoidal graph a sine minus omega t or minus of a sine omega t. The period of oscillation of the wave is the time taken for an element to complete one full oscillation. That is, minus a sine omega t can be represented as minus of a sine omega t plus capital T. Since the sine function repeats after 2 pi, omega t is equal to 2 pi. Or we can write omega as 2 pi by t. Omega is the angular frequency of the wave. The frequency nu is the number of oscillations per second. Therefore, nu is equal to 1 by time period or omega by 2 pi. The SI unit of time period is seconds, SI unit of omega is radians per second, and of frequency is hertz or second inverse. In the discussion so far, we have considered only waves along a straight line, that is transverse wave. In longitudinal waves, the displacement of an element in the medium is parallel to the direction of propagation of the wave. The displacement function of the longitudinal wave is written as x of st is equal to a sine kx minus omega t plus phi, where s of xt is the displacement of an element of the medium in the direction of propagation of the wave at position x and time t. A is the displacement amplitude and other quantities have the same meaning as in the case of the transverse wave, except that y of xt has to be replaced by x of st. We have seen how we can characterize a progressive wave by quantifying its components. What other information is hidden in the mathematics? Let's find out in the coming sessions. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.